Hi everybody, this is your lecture 5 part 2. So in this part we're going to see how to solve probability problems using tree diagrams. Okay, so I know that you would have done problems using tree diagrams in school, but we are going to see this in a different angle again. That is, we're going to concentrate on problems involving condition probabilities. So you're going to see how to use tree diagram to solve probability problems with conditional probabilities. Yeah, that is probability without replacement. So we are going to stick to the same style of examples so that you can finally apply that to real world problems. Okay, so let's see what is tree diagram first. Tree diagram is a simple way of showing probability problems which involves combination of two or more events. So for example, let's stick on to the same example. Here we have a bag of green and blue balls. So when you have such an example where you have to pick two balls, then this means there are different possibilities, and therefore you can determine the probabilities of the different possibilities. Yeah. So here you can, in the first event, you can either pick a green ball or a blue ball. Yeah. So the probabilities are given along the branches of the tree. I mean, branches of this tree, yeah? Because it looks exactly like the branches of the tree. So what I mean is here, the probabilities are given along the branches of the straight line. Yeah. So you give the probabilities along the straight line. So for example, what is the probability of picking a green ball from here? It is the total number of balls is 1, 2, 3, 4, 5, 6, 7, 8. So there are 3 ways you can pick the green ball out of the 8 balls. Okay. Similarly, what is the probability that you can pick a blue ball? There are 5 ways you can pick the blue ball. So it is 5/8. Now, if I have a second event, like after picking the first ball, and if I replace the ball, I put this ball back again, I can pick another ball, and that ball could be green or blue. So there are 2 possibilities. So I write the probabilities on the side of this straight line. So for example, if I replace, this is all by replacing the ball, okay? If I replace this ball, what is the probability that I'll pick a green ball again? It's going to be 3/8, okay? What is the probability that I'm going to pick a blue ball? It's going to be 1, 2, 3, 4, 5. So 5/8. What is the probability I pick a green ball after blue ball? It's going to be 3/8. What is the probability that I'm going to pick a blue ball after I pick a blue ball? It's going to be 5/8. It's because I have replaced the first ball. Okay. So this is how you write the probability along the straight line. Now, towards the end of the branches, you write the total probability. That is, what is the probability that I pick a green ball and then a green ball? That's going to be, it's an AND process here. So 3/8 times 3/8, which is nothing but 9/64. Similarly, what is the probability that I'll pick a green ball and then a blue ball? It's going to be 15/64. Now, what is the probability that I'll pick a blue ball, then a green ball? It's going to be 15/64. What is the probability that I will pick a blue ball and a blue ball? It's going to be 25/64. So that's how it helps you to see the probability. The tree diagram clearly helps you to see the probability. So what happens is 9/64 is the probability of picking both balls green by replacing the first ball. Similarly, 15 by 64 is the probability of picking first ball as green and second ball as blue. That is by replacing the first ball. Okay, similarly, again, first ball is blue, second ball is green. The last one is probability of picking both balls as blue. First ball is replaced. Okay, so that clearly tells you how you have, clearly tells you the different possible ways you can pick a ball and the probabilities corresponding to that. Yeah. Okay. So this can clearly help you understand whether the two events are independent or not independent. Okay. So what we have just seen is by replacing the ball, that is two independent events. Okay. Now let's see what happens if we don't replace the ball. That is conditional probability, not independent. Okay. Okay. So in the last week, we have seen what is condition probability and how to represent the condition probability. Yeah. That is when the probability of a second event occurring is affected by the outcome of a first event. Yeah. When it is not independent. We have seen what it is. Yeah. And how we represent it in using probability notation. Now let's take an example to understand this for a tree diagram. Yeah. So we have a question here. A bag contains 3 green balls and 5 blue balls. A ball is selected at random and then a second ball is selected without replacing the first ball. Find the probability that the second ball is green. If I had asked you this question last week, you would have used the multiplication rule to solve this conditional probability problem. So why don't you try that now and find the probability that the second ball is green? Good. Now let's see how to solve the same problem using a tree diagram. Okay. So we have a bag containing 3 green balls and 5 blue balls. So we're going to draw a tree diagram. So let's start with the bag. There are 2 ways we can do this. We can either pick a green ball or a blue ball. And the probability of picking a green ball will be 3 by 8. And probability of picking a blue ball will be 5 by 8. Now, without replacing the first ball, there are 2 possibilities. You can either pick a green ball or a blue ball. And the probability will be 2 by 7 and 5 by 7. Yeah. Similarly, you can either pick a green ball or a blue ball. And the corresponding probabilities. We have done this before. We are just doing the same thing using tree diagram. And towards the end of the branches, you can write the probabilities, the total outcome. Yeah. So let's do that. Yeah. So probability of both balls green will be 3 times 2 over 8 times 7. So 3 times 2 is 6, 8 times 7 is 56. Now what is the probability of picking a green ball first and then a blue ball second? Without replacing the first ball. It's going to be 3 times 5 is 15, 8 times 7 is 56, isn't it? So probability of picking a first ball green and the second ball blue is 15 by 56. Now, what is the probability of picking the first ball blue and the second ball green? It's going to be 5 times 3, 15, 15 by 56. What is the probability of picking a blue ball first and then a blue ball? Remember, without replacing the first ball. It's going to be 20 by 56. Okay, so now you have put all the outcomes towards the end of the branches. One important thing, when you add all the possible outcomes of selecting the 2 balls, what do you get? Add them all. 6 by 56 plus 15 by 56 plus 15 by 56 plus 20 by 56. What is the total possible outcome? What is the total probability? 1. Yes, that's right. The total probability is 1. Okay. It's very important you understand that, yeah? Okay. Now find the probability that the second ball is green. How will you do that? Okay, let me erase all these things. What is the probability that the second ball is green? Let's look at here. Yeah. You have here the second ball is green and here the second ball is green. So you can either pick this way, that is green and green, or you can pick blue and green. There are two possible ways you can do that. Yeah. So that means what is the probability of picking the second ball as green? It is 6 by 56 plus 15 by 56, because there are two possible ways to do that. And what do you get? 6 by 56 plus 15 by 56 is 21 by 56. And you can simplify it to be 3 by 8. Okay. Okay. So that's how you do problems, especially for conditional probabilities. Yeah. Okay. Now let's see something more which you use in biology or other subjects. Yeah. A real life. Given 15%, 50% of the population are male, if the probability of a male being colorblind is 1 over 15, what is the probability of a female being colorblind? No, not what is it. And the probability of female being colorblind is 1 by 100. Sorry, guys. Is 1 by 100. Now the questions follow now, okay? Draw a tree diagram to represent this situation. What is the probability that a newborn baby is colorblind? Given a newborn baby is colorblind, what is the probability it is female? Explain why being colorblind is not independent of gender. So what I want you to do is now is pause the video and draw a tree diagram and then answer part B, part C, and part D. Good. So this is how your tree diagram will look. Random birth. You're starting with, you don't know, it could be a boy or it could be a girl. So it could be a male or a female, yeah? So we have seen that the probability is 50% male. That means the female should be 50%, yeah? So 50-50%. Then you have two possibilities. The male, the child born could be colorblind or a normal child. So you have two more branches, normal and colorblind, okay? So you have two more branches and then you write down the respective probability because I'll show you there, yeah? So you have 50-50%. So 50% male, 50% female. If the probability of being colorblind is 1 over, male being colorblind is 1 over 15. So male being normal will be 4 over 15, isn't it? 14 over 15, isn't it? Yeah, 1 over 15, so 14 over. So because 1 plus 14 is 15. Similarly, if the probability of a female being colorblind is 1 over 100, that means female being normal will be 99 over 100, isn't it? Yeah, because it is 99 plus 1 is 100. Here it is 14 over 15. Because 14 plus 1 by 15 is 100%. Yeah. Okay, so that's how you branch the tree. So this probability together will give you a probability of male and colorblind. And what will it be? 1 over 30. What is the probability of having a male that is normal? 14 over 30. Yeah. What is the probability of getting a female colorblind? 1 over 200. What is the probability of getting a female and a normal child? So it's going to be 99 over 200, yeah? Okay, so that's how it is. Now what I want you to do is add them all and check the probability, guys. What is the probability? Oops. Good, 1. Yeah, it has to be 1, yeah. Okay, now let's go to so you have completed the tree diagram. Now let's answer all the questions. Okay. Yeah, the sum should be 1 because they are mutually exclusive, yeah? Okay. What is the probability that a newborn baby is colorblind? Let's do this question now. Yes, that's right. For probability of a colorblind, there are two ways it is possible, 1 by 30 or 1 by 200. So you add them both You get 23 out of 600. Next question. Given a newborn baby is colorblind, what is the probability it is female? Okay, this is like a conditional probability. So you have to be careful. You can write down the formula first. Yeah, because you haven't done the other way. Yeah, here. So this here it is female, then normal. Yeah. So given that the newborn baby is colorblind, what is the probability that you're going to pick a female child? So that means using the formula, conditional probability formula, you have female intersection colorblind over colorblind. So what is female and colorblind? That's here. And what is the probability that you pick it colorblind? You already calculated, that was 1 over 30 plus 99 over 200, isn't it? No. Yeah. 1 over 200 plus 1 over 30. That is this. Okay. So that is the probability of getting a colorblind baby. Yeah. So you write down what is female intersection colorblind and divide it by 23 over 600. And then you get the probability, conditional probability. Yeah. Okay. Next, the last one, I think. Explain why being colorblind is not independent of gender. So you have to show the rule, which we learned last week. Yeah. So you calculate this, and you have already calculated that, and you got, see, that's the previous question. You already calculated, you got 3 over 23, and then check whether this is equal to probability of female. So what is the probability of picking a female? 50%, isn't it? And that is probability of just picking a female. Yeah, it is 50% chance. You can see clearly that this is not equal to this. So the two events are not independent. Yeah. So being colorblind is not independent of gender. Okay. So now we have seen few problems, how to solve using Venn diagram. Now you can use what you've seen. I mean, you've also seen how to use tree diagram, problems solving using tree diagram. So what I want you to do now is for the same problem, for the same tree diagram, why don't you try out the Venn diagram? Pause the video and try it out. Good. Yeah, what I've done here is I've chosen male as A and colorblind as B. Okay. And we know that if we choose male as A, that means A prime should be female. And if we choose B as colorblind, B prime should be the normal baby. Yeah. And this area is A intersection B, probability of A intersection B. And this area will be probability of A intersection B prime. This area will be probability of A prime intersection B. And this area will be probability of A prime intersection B prime. Yeah. Okay. And then you can corresponding probabilities you can fill in. Yeah. You know that what is male and colorblind. That's this, male and colorblind. So you can fill 1 over 30 there. Male and normal. Male and normal. Yeah, that is 14 over 30. That's going to be male. So normal is B prime. Can you see that? So male and normal is this. So you fill there. Female and colorblind. Female is A prime. And colorblind is this. So A prime and so female and colorblind. You can fill that. Similarly, female and normal. Female is A prime, normal is B prime. So you can fill that here. That's it. So this is how you can convert a tree diagram into a Venn diagram. Similarly, you can convert a Venn diagram into a tree diagram. And you can convert them into a two-way table too. Yeah. So we're going to do more problems like this in seminars. Okay, that's all for now. Thank you, guys.